All right, everybody. So today we're going to talk about gas stoichiometry, which is really no different than any other form of stoichiometry. We're still going to be using a mole ratio. The only difference is that because gases are often measured using their volume, we're going to be able to calculate the volume of gases that's produced in a chemical reaction. Okay, so first off, we have to discuss the kinetic molecular theory a little bit. Remember that all gases have the same behavior. So we talked about the behaviors of gases already a little bit. We said that gases have tiny particles. In fact, the size of the particle doesn't matter because compared to the space between the particles, the volume of a gas is vastly going to be made up of the space rather than the particles themselves. So the particles almost make up none of the volume of a gas. In addition to that, we know that we can use the ideal gas law for all of these gases. And so what that means is all gases have the same volume at the same temperature and pressure. Okay, so if I have 1 mole of any gas, it doesn't matter the identity of the gas, whether it's hydrogen or helium or sulfur hexafluoride, which is much, much heavier than either one of the other gases. It really doesn't matter because all of them are going to behave the same. The particles are constantly moving. The particles really take up almost none of the space. It's the space between the particles that makes up the volume. Whenever they are heated, they are all going to expand. The space between the particles is going to grow. Whenever they're cooled, then the particles slow down and the space between the particles becomes smaller. So really, the identity of the gas doesn't matter. We're able to use kind of the same calculations for all of them. That being said, it does not matter the identity of the gas. We are able to use this conversion factor. 1 mole of any gas, it does not matter the identity, is equal to 22.4 liters of volume as long as that gas is at STP. So as long as the temperature and the pressure are at standard conditions, so the temperature is 273 Kelvin and the pressure is equal to 1 atmosphere, then it does not matter what gas I have. If I have a mole of it, it's going to take up 22.4 liters of space. Okay, so we can use this conversion factor for all gases. It does not matter what gas I have, as long as the conditions are at STP. Okay, now obviously we've talked about it. If the temperature goes up, then this volume is going to go up. If the pressure goes up, then this volume is going to go down. So we've talked about how temperature and pressure will affect volume. So we are going to talk later on about how we deal with volume of gas whenever the conditions are not at STP. But as long as your problem tells you that your gas is at standard conditions, it's at STP, then you can use this conversion factor, which means we can update our mole map just a little bit. We've had mass conversions when we're doing stoichiometry. We've done those. We've started with moles. We've started with particles. And now we can start with the volume of gas. Again, as long as it's at standard conditions, standard temperature and pressure. Okay? We know that if we're given a mass to start our problem, then we have to use the molar mass as a conversion factor before we can do the mole ratio in that problem. If we're given moles, we can just skip straight to the mole ratio. There's nothing to convert. If we're given particles, we know that 1 mole is equal to 6.02 times 10 to the 23rd particles. So we've done problems where we've started with particles and used Avogadro's number to convert it to moles before we use the mole ratio. And now what we're going to do is we're just going to add this. If I am given a volume of a gas at STP, then I can use my new conversion factor. 1 mole is equal to 22.4 liters of gas. That way I can convert my liters of gas to moles and then use the mole ratio. Okay, now if I'm trying to get mass or moles or particles, we use those same conversion factors, right? We just kind of flip them around at the end because we're trying to convert from moles to mass. So I put 1 mole on the bottom this time. Molar mass should be on top. Okay, if you're trying to get an answer in moles, then after the mole ratio, you're done. If I want my answer in terms of particles, then of course we use Avogadro's number, right, to convert moles back to particles. And then if I want my answer in liters, as long as the gas is at STP, then I can use my new conversion factor. 1 mole is 22.4 liters, okay? So I have a practice problem to show you guys kind of how this works. It's still stoichiometry, and so it's still going to be kind of the same steps that we've always taken. The first thing is, look at your problem. 5 grams of C3H8 is burned in oxygen. What volume of carbon dioxide should be produced at STP? So these are the magic words right here. If I know that my gas is being produced at STP at standard conditions, then I'm going to be able to use that conversion factor. The 1 mole is equal to 22.4 liters. So I'm going to be able to use that conversion factor, okay? Now it's still stoichiometry, and stoichiometry always starts with a balanced chemical equation. And so if I look at this equation, I have 3 carbons. So I need 3 carbons on the product side. I have 8 hydrogens. So I need to make 8 hydrogens on the product side, which means 4 times 2 is 8. So I have to put a 4 there. And then if I add up all of my oxygens, I have 4 here, plus 3 times 2, 6 more here. So that's 10 total on this side of the equation. I need 5 oxygens on the reactant side to balance that out. So our equation should be balanced, okay? So again, stoichiometry always starts with that balanced chemical equation. And then I look and I say, okay, well, I'm starting off with 5 grams of C3H8, so that's going to be my starting point. And the question is, what's the volume of CO2? All right, so I'm starting with C3H8, but they're asking me something about CO2. So my mole ratio, if I look at it, it's going to be 1 mole of C3H8 for every 3 moles of carbon dioxide. So that'll be the mole ratio that I use when the time is right, okay? We're going to start the problem with the 5 grams that we're given. So 5.00 grams of C3H8. If I'm starting with grams, then I need to drop that unit down. And anytime that I have grams, I know that I need to look at the periodic table. So if I add together 3 carbons and 8 hydrogens, we get 44.097. And so again, that's equal to 1 mole of that substance, C3H8. Okay. But I didn't just want to convert grams to moles. I need to actually convert C3H8 to carbon dioxide. So now I'm going to drop my unit down. And once I have moles on the bottom of my dimensional analysis, I know that it's time for that mole ratio. So 1 mole of C3H8 is equal to 3 moles of carbon dioxide. And if I look, I want my answer in terms of volume, right? So volume is liters. I need liters at the end. Since my gas is at STP, I'm going to be able to use this conversion factor. 1 mole. In this case, it's carbon dioxide, but you can use this conversion factor for any gas. 1 mole is equal to 22.4 liters. So if I look at this, I'm going to drop my unit down. Mole CO2. 1 mole of carbon dioxide is equal to 22.4 liters. So really it's the same, we just get to use a new conversion factor for liters of gas. As long as the problem says that the conditions are at STP, then we can use this conversion factor in our dimensional analysis to get the answer. And if we multiply across the top and then divide that product by the bottom, then our answer is going to be 7.62 liters of carbon dioxide. Okay? Now the question is, what if the gas is not at STP? So oftentimes gases are collected not using standard conditions. So if we look, this problem is a little bit different. I still have 5 grams of C3H8. It's burned in oxygen. The question is, what volume of carbon dioxide will be produced at 500 degrees Celsius and 2 atmospheres? So STP means that your gas is at 0 degrees Celsius and 1 atmosphere. Obviously, this is not STP. This is not standard conditions. So here's what we're going to do. We're still going to start our dimensional analysis the same way, but we're going to stop doing dimensional analysis after the mole ratio. So it's going to be a lot like the problem up above. I'm still starting with 5 grams, converting it to moles, and then converting moles of C3H8 to CO2. But that's where I'm going to stop. Okay? What I'm going to do then is calculate moles. And then I'm going to use the ideal gas law. Okay, so remember that the ideal gas law is PV equals nRT. So basically what we're going to do is we're going to do dimensional analysis to get moles, and then we're going to plug that value in for N in the ideal gas equation. And so we have a pressure of 2 atmospheres, we can plug that in. We have a temperature of 500 degrees Celsius, we'll convert that to Kelvin and plug that in. We always have a value for R, we just look that up. And then we can solve for volume. So since our gas is not at STP, we cannot use this last conversion factor. So instead we're going to stop just before it, calculate moles, and then use the conditions we have to fill in the ideal gas law and solve for volume. So just to show you how it works, I'm going to start again with my known value. Drop my unit. From the periodic table, it's 44.097 is the mass of 1 mole of C3H8. I drop my unit again because I need to keep going. 1 mole of C3H8 produces 3 moles of carbon dioxide. And that's where we stop. We have to stop there because we're not able to convert moles to liters. Our gas is not at STP. So instead we're going to stop there at moles and go ahead and calculate. So if I multiply across the top and then divide by the bottom, I end up calculating that there's 0.340 moles of CO2 produced. So that's how many moles I have. Then I have this temperature and this pressure. I can plug those numbers into the ideal gas law and solve for volume. So if I go ahead and do that, the pressure was 2.0 atmospheres. We don't know the volume. We just calculated moles using stoichiometry. We have 0.340 moles. Since the pressure was given in atmospheres, then I'm going to use 0.0821 as my value for R. Remember that if your pressure unit is different, then you use a different value for R. And then the temperature is 500 degrees Celsius, which we have to convert to Kelvin. If I add 273, then I end up with 773 as my temperature. So then we multiply the side that's all numbers and take that product and divide it by 2, right? So it'll be this product divided by 2 because that's the variable side. And so when we do that, we end up with a volume of 10.8 liters. Looking at the numbers that I was given though, it seems to me that 2.0 atmospheres is only 2 significant figures, so I'm going to go ahead and round this to 11 liters. That would be the volume of carbon dioxide that's produced under the conditions that we were given. So hopefully this becomes clear to you guys. We are going to practice this. It's really not much different than stoichiometry we've done. It's just that you may have to stop your stoichiometry a little bit early and use the gas law to get your final answer.